Welcome to homework.
We want to find the pressure at A, the pressure at B, and pressure at C. Rather, pressure at A is given, but pressure at B and pressure at C. So we know that we have a monatomic gas, which means that our gamma value is going to be equal to 5/3. And we can say that P sub B, V sub B divided by T sub B is going to equal P sub A, V sub A divided by T sub A. And this is simply due to the ideal gas constant. And so P sub B would be equal to P sub A, V sub A, T sub B divided by V sub B, T sub A. And we can solve. So the pressure at A is 1 atmosphere. The volume at A is 22.4 liters. Volume at B is 56.0 liters. And then the temperature at B would be 273 Kelvin. Temperature at A would be 273 Kelvin as well. The process from A to B is isothermal. So we can say that the pressure at B would be equal to 0.400 atmospheres. Now, for the pressure at C, we can say that for the adiabatic compression, in this case, we can say that P sub A, V sub A to the gamma power would be equal to P sub C, V sub C to the gamma power. So P sub C would be equal to P sub A times V sub A divided by V sub C to the gamma power. This is equaling 1 atmosphere times 22.4 liters divided by 56.0 liters to the 5/3 power. This is giving us a pressure at C of 0.217 atmospheres. So this would be our answer for the second answer for part A and our first answer for part A. So for part B, we want to find the temperature at C. So we can say P sub B, V sub B divided by T sub B is equaling P sub C, V sub C divided by T sub C, which means that T sub C would be equal to P sub C, V sub C, T sub B divided by P sub B, V sub B. These are going to cancel out, and this equals 273 Kelvin, the temperature at B, and then times 0.2172 atmospheres divided by 0.400 atmospheres. And we find that T sub C is going to equal 148 Kelvin. That would be our answer for part B. And finally, for part C, we need to find the work done and the heat transfer. Rather, just find the we're in the process of we're going to be finding the change in internal energy, the heat transfer associated with each process, and the work done in each process. So we can say for process AB, we can say that the change in internal energy for AB would be equal to the number of moles times the molar heat capacity at a constant volume times delta T. And we know that this is 0 because this is an isothermal expansion. So we can say that the heat transfer associated with this process would be equal to the work done. And this would be equal to nRT times the natural log of the product, rather of the quotient of the volumes. And so we can say that Q A sub B, which again equals work AB, would be equal to 1 mole times 8.314 joules per mole per Kelvin times 273 Kelvin multiplied by the natural log of 2.5, and this is equaling 2080 joules. For the change in entropy at AB, we find that this is going to be Q sub AB divided by T sub AB. So this would be equal to 2079.7 joules, and then divided by 273 Kelvin. This is equaling 7.62 joules per Kelvin. At this point, we can say for process BC, we know that the work done in BC would be equal to 0 joules because this is an isochoric process, so constant volume, no work is done. This is C. And then we can say that the change in internal energy of BC would be equal to Q sub BC, the heat transfer associated with that process, and this would be equal to the number of moles times the molar heat capacity at a constant volume times the change in temperature, and this is going to equal, rather we can say Q sub BC will equal 3 over 2 nR delta T, and this will equal 3 over 2 times 1 mole times, again, 8.314 joules per mole per Kelvin, and then times the change in temperature, 148 minus 273 Kelvin, and this is giving us negative 1,559 joules. At this point, we can find the change in entropy associated with BC, and this will be equal to the integral from B to C of dq over T. This is equaling T at B, T at C, 3 nR over 2 times dt over T. And we can solve. So we can say that the change in entropy at BC would be equal to 3 times 1 mole times, again, 8.314 joules per mole per Kelvin divided by 2 times the natural log of 148 divided by 273, and this is equaling negative 7.64 joules per Kelvin. Now we finally go on to process CA. For process CA, we know that this is an adiabatic process, therefore the heat transfer is going to be 0 joules, and we can say that the associated entropy change is going to also be 0 joules per Kelvin because the heat transfer is 0 joules, therefore the change in entropy is 0 joules. Again, this is because the process is adiabatic. Knowing this, we know that the change in internal energy associated with CA will just be equal to the negative work done, and this would be equal to negative 1 times the change in internal energy associated with AB minus the change in internal energy associated with BC. So this will equal negative 0 minus negative 1,559 joules. Therefore, the change in internal energy associated with process CA would be positive 1,559 joules, while the work done for CA would be equal to negative 1,559 joules. Finally, we get to part D, and part D is simply asking for the efficiency. So the efficiency is going to be the work done divided by the input energy. So this would be 2,080 joules minus 1,559 joules divided by 2,080 joules, and this is giving us 0.250. And so our efficiency equals approximately 25%. This is our final answer for part D. That is the end of the solution. Thank you for watching.